All right, so number 3, also great because it is not super heavy on calculations, even though it is a probability question. It's getting at some important ideas, but it is really heavy on understanding. So first things first, let's just read through and see what we're dealing with. We've got a lake with 2,000 fish in it. The distribution is approximately normal. So I'm going, yes, I know the normal distribution, I'm good. The claim is that the mean length of fishes is 8 inches. So generally when we see claim, we're thinking hypothesis test. But then it says, if this claim is true, which of the following is more likely? So kind of like saying a hypothesis test, right? If this is the null, if it's true, which is more likely? So the question is a random sample of 15 fish having a mean length greater than 10, or a random sample of 50 fish having a mean length greater than 10. So we have to do a couple of things here. One, we have to recognize that we're talking about a sample mean, right? So we're basically saying what's the chance that X bar is greater than 10 in these two different scenarios. It's the same exact cutoff, right? We're still looking at greater than 10. The only difference is a sample of 15 versus a sample of 50. So we need to make sure that we answer this and that we justify it, right? So more likely, a sample of 15 is more likely to have this blah, 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 blah. My justification. Now, I haven't looked at the actual answers, but my guess is there's probably a number of things you could do here. One is we could talk about variability. We know as n increases, the one thing that changes about my sampling distribution of a sample mean is the variability, right? You could say something about smaller sample size mean we're going to have less spread away from the true value of the average, right? We're going to have a smaller standard deviation. You could even go so far as to bring up the fact that we know the standard deviation of a sample mean is the original standard deviation divided by the square root of n. So if we divide by a bigger n, we'll have a smaller standard deviation, right? So we could sit there and draw out both these curves are going to be centered at 8, but this one's going to be way smaller, centered at 8. So 10 will end up further over. You could even bring it back to a z-score and talk about that z-score would be larger. You could make up a standard deviation as your justification. They didn't give you one, so you were kind of stuck here, and you really had to understand this idea that the standard deviation is going to shrink. And if my standard deviation is smaller, a value away from the mean is more unusual, right? So if you needed to demonstrate it to yourself, I think it would have been completely fine to just make up a standard deviation and calculate it both ways, right? You could have found yourself two different probabilities using normal CDF. But the heart of this whole question was this standard deviation of our sample mean and how it changes. It becomes less spread out. They're both going to be normal because we started out normal, approximately normal. It's just a matter of the spread of these two distributions. And again, this brings us kind of back to the number 1, right? We're comparing two things, and we're kind of almost back to socks. The shape is the same, outlier situation is the same, center is the same because they're both going to be centered at this 8, but the spread is different, and we're going to use that as our justification. All right, so part B says, suppose now we know the standard deviation is 0.3 inches. So we could always use that and go back to A if we were sitting there kind of unsure about A and see just what that calculation would look like. But we got the standard deviation. Oh, and this is the standard deviation for the sample mean of size 50. So they're actually giving us this. We don't have to do all of the work of dividing by the square root of 50. If the mean length is 8 inches, use the normal distribution to compute the probability that a random sample will have a mean length less than 7.5. So we know we're dealing with normal. We're looking for a probability. So I'm going to draw myself a cute curve. Remember, this is the crucial thing in terms of the AP. For these normal questions, you need to make sure you hit all those parts of the rubric because it tends to be pretty set. So we need to make sure that if we draw a normal, okay. All right, so remember with those normal distribution questions, we do need to make sure we've defined our mean and our standard deviations. So we've got our mean of 8. We can do that either by just writing mu equals sigma equals, putting it in the calculator speak with mu equals sigma equals. We do need to have a cutoff and direction, so you either rewrite your answer with less than 7.5 or You draw it on your curve. That's completely fine, 7.5, and you shade less than. That'll also get you cutoff and direction. You could even use the probability notation. We didn't use that often, so I'm not going to. But now we're just using the normal calculator, right? Normal CDF, E99, which again, the other way to get our direction and cutoff would be to say lower equals negative E99, upper is 7.5. That'll also give me mean and direction. But cutoff and direction. Those are the things. We need to make sure we have something to show normality. Our curve will do that. Writing normal is good. Mu and sigma defined, necessary. And then our mean and cutoff with the direction and cutoff with the correct calculation. Bah, my calculator's not opening on the screen, so I'm going to go grab one. So for finishing this question with the calculator, since I can't put my calculator on the screen, we're going to do normal CDF. I'm just going to go ahead and label everything because it's good practice for the AP. For the lower, I put a negative E99. The upper, I'm going to do 7.5. The mean, 8. And the standard deviation, the 0.3. This is definitely one where I could see you maybe not spotting that they actually gave you the standard deviation already for the sample mean, and you maybe went too far and did a second screw to 50. Not to worry, that would only knock you in the parameters portion and you'd still get your P, right? So if you do this, we get 0.0478. And again, don't worry too much about rounding. The AP is pretty generous as long as you have shown all your work. It's more about the communication than it is the end value. All right, so that's part B. Yeah, so I finally glanced at the rubric for A. A definitely has, you said the answer, and then you used a justification related to spread or variability. Great. B says that you got the right value and you have some work to show that you did something to get that value. So they didn't even have you do all of the normal work in terms of showing everything. So if you had just had that curve and then 0.0478, looks like you would have gotten fine an E on this. If you accidentally divided again by the square root of 50, they specified that that was a P. So that was how the rubric broke down. Again, I recommend we just go with the anal retentive rubrics of the more recent tests, and we make sure we define our parameters, our cutoff, and our direction, as well as give the actual probability. All right, so part C. Suppose the distribution of fish is non-normal. Ooh, so now they're saying it wasn't normal to begin with, but had the same mean and standard deviation. Would it still be appropriate to use the normal distribution to compute the probability in part B? Justify your answer. So we need a couple of things whenever we're dealing with our samples, right? This is basically, would it be appropriate is another way to say, did we meet those conditions? So let's remind ourselves of our conditions for all of this stuff in part 7, because that's essentially where we are. We're in sample mean land part 7. And even if we weren't, we know our 4 conditions. SRS, independence, and this is going to be overkill. I just want to put it all down there because it's fairly important. So n is less than 10%. That gives us that independence. And then we don't have a P, right? This is about means. So we either need normal or n is greater than or equal to 30. So if I was going to be really good about this, I would check each and every one of these. So I would say, okay, well, did they say they were taking a random sample? Yes, it says random sample. If it's a random sample, we should have independence, but let's check our n is less than 10%. 50 is less than 10%. Oh, they actually told me how many fish were in the length. 2,000. So it is less than 200. We do have this, which means because of both of these things, we have independence. Like I said, this typically is not on the AP, but it's just one of the things I have you check. So the last one, and this is the only one they actually checked on the rubric, is that since we don't have normality, we should have an n greater than or equal to 30 to be able to use the central limit theorem. So in this case, we had an n of 50, so we do have this. So we need to make sure we answer the question, is it appropriate? The answer is yes, because the conditions are met. And then I could just point over here to all this work I already did. So all that stuff we did with our hypothesis test, excellent. We can just go ahead and point to that. Now, when you look at the rubric for part C, they basically said you need to say yes, have a justification that involves the fact that our sample size is large, which we do, and then you need to mention the central limit theorem. So mentioning the central limit theorem in words, right, that the sample mean will be approximately normal as long as my n is greater than or equal to 30 is legit. I'm not sure how many of you guys would actually write the central limit theorem, which is the whole thing that gives us this, and I don't think they would have required you to actually have that particular theorem listed by name. But the central limit theorem is what gives us normality when we have a large sample size, with both proportions and means, because technically proportions are a mean of a bunch of ones, like if you thought of them as being coded as 0, 1. So the central limit theorem is what this one all came down to. They didn't require you to check anything except for this last piece here, but I still think it's good practice whenever they ask, is it appropriate? Are the conditions, like, right, that we're checking the entire conditions. Appropriate tends to mean we're either talking about conditions or we're talking about how the sample was taken. And in this case, it was just a random sample, so that wasn't the issue. It was whether or not we had the required pieces to be able to use a normal distribution.